Thank you all for attending this presentation of the paper titled OPF-based under-frequency load shedding, predicting the dynamic frequency trajectory. The paper has been co-authored by my colleagues Quentin Walger, Yihui, Guglielmo Frigo, and Mario Paolone, all from DESL EPFL. So within the context of optimization methods for the planning and operation of power systems, the definition of the objective function and of the problem constraints differ depending on the target application and on the available time budget. Now, optimization-driven controls rely on the use of optimal power flow equations that, by definition, are static in order to define the associated optimal power flow problem. However, time-dependent constraints could be also included in order to formulate a time domain OPF that guarantees the feasibility of the determined control actions together with the time domain trajectory of the network state. For instance, the paper in the bottom reference that was presented a few PSCC back is along this trajectory of paper. Now, also our work is along this trajectory and deals with the problem of determining the least amount of load to be shed after a large power system contingency in order to keep the system safe from the frequency and from the line congestion perspective. Now, in general, UFLS methods rely on local control strategies, and they do not take into account the state of the entire network. They set their decisions on parameters that have been predetermined according to some predefined values. However, the single constraint on the frequency does not prevent from further violation of safety limits of, for instance, node voltages or line and transformers currents, and therefore does not prevent the cascade tripping of further generators. Now, in this context, the coupling of a UFLS scheme with the OPF problem represent a promising solution, especially when it is combined with a model that is capable to predict the system dynamics. The proposed method is meant to enhance the performance of the emergency operational practices in TSO control rooms. The method leverages on the real-time situational awareness provided by phasor measurement units, PMUs. It is reasonable to assume that the network model, combining the network topology and electrical parameters of the network components, is assessed in real time in the TSO control room. Now, based on the network model and on the gathered synchrophasors, the system state can be estimated in real time with time delays in the order of hundreds of milliseconds. Now, based on the results of the state estimation, the proposed UFLS method runs in parallel to conventional contingency analysis in order to predetermine a UFLS strategy that can happen for each possible contingency. The proposed method is based on the following assumptions. So first, the nodal admittance matrix, the network topology, and the network parameters are known in real time. Then that the system state is also tracked in real time by means of PMUs that feed a state estimator. The controlled variables are the average system frequency, the node voltage phasors, and the line current phasors as provided by the state estimator, whereas the control variables are the loads to be shed in terms of active power in each load bus. The amount of loads to be shed is determined by solving the following optimization problem, where we minimize the total amount of loads to be shed subject to 5 categories of constraints. The first ones are the grid constraints, comprising frequency, voltage, and current limits. Then we include a dynamic system frequency response in order to track the frequency evolution in the time domain. We further include active and reactive power outputs of generators and loads, and we finally consider the power flow equations. Now, in the next slides, I will discuss each of these constraints, and in particular, I will discuss the simplifications that we introduced in order to achieve a convex and tractable formulation. I would like also to mention that we are currently working on an extension of this study where we track also the evolution of other variables in the time domain, and we make fewer assumptions while still achieving a tractable formulation. Frequency, voltage, and current are bounded in a hard way by known quantities, which is pretty standard. And then after a generic contingency, what we do is that we predict the frequency trajectory due to the power imbalance given by the loss of the generators and to the subsequent load shedding by means of an equivalent frequency dynamic response model. We assume a single area equivalent where all generators swing synchronously at a common frequency, and therefore we get an equivalent single machine swing equation that is inversely proportional to an equivalent inertia response. And we also consider an equivalent damping factor for the whole area. As regards the generators, their active power is determined based on the generator's droop characteristic only. Indeed, in order to make the problem mathematically tractable, we neglect the response of the governor, the prime mover, and the secondary frequency regulation. The reactive power instead is computed as a function of the active power scaled to a voltage-dependent factor. As regards the loads, we consider the Electric Power Research Institute load-scene model, where load, active and reactive powers are voltage and frequency dependent. Now, these load equations are linearized around the precontingency set point in order to achieve linear formulation. And also, in order to achieve a tractable formulation, we consider their asymptotic values only. We determine the node voltages and the line currents as a linearized function of the nodal power injections using the sensitivity coefficient method that is presented in the bottom reference. Now, from these equations, we assume that the system operator knows in real time the model of the grid, therefore the Y nodal admittance matrix, as well as the system state, namely the voltage phasors in all buses. Therefore, as you can see in these equations, the only unknown are these partial derivatives. These coefficients can be assessed in real time, as shown in the bottom reference, and where it is also demonstrated that the solution is unique. Now, by knowing these sensitivity coefficients, it is quite straightforward to derive the power flow equations, where we approximate the voltage and current variations as a linearized function of active and reactive power and generator voltage magnitude variations. And now I leave the floor to Yihui.
Thank you, Asja. In the first part, we have presented the proposed OPF-based UFS method. In the second part, we are going to show the validation of the proposed technique. In order to perform the assessment, we use the OPRT in Maxon Power Grid Real-Time Simulator to implement a full replica dynamic model of the IEEE 39-bus power system, which is also known as 10-machine New England power system. This benchmark power grid has been widely employed for evaluating and comparing the system operation and management practices. It consists of 10 synchronous generators, lighting nodes, with a nominal voltage of 345 kilovolt. At each bus, we also implemented a simulated PMU to obtain system state estimation. In this work, the proposed UFS approach is tested for the contingency of 2 generator outage, causing in total 1,100 megawatt power tripped. For the same contingency, we consider 2 scenarios. In scenario 1, the system constraints are largely satisfied, which means the pre-contingency line currents are far from the ampacity limits. For the scenario 2, the pre-contingency currents of line 2 to 3 and line 13 to 14 are already close to the ampacity limits, so there are high risks of ampacity limit violation during the contingency. For the purpose of comparison, the results are compared with the results using the UFS strategy recommended by NSOE. The UFS strategy recommended by NSOE is a local control scheme. Hereafter, we call it as the standard UFS. As you see in the graph, the loads are shared proportionally to the measured frequency. Here are the results for the scenario 1, when the ampacity limits are not bounded. As we see from the frequency curves, both UFS strategies constrain the frequency from going below 49 Hz. The blue curve is the true value of the frequency when applying the proposed UFS obtained from the real-time simulation. And the red curve is the predicted frequency trajectory by the proposed method. The yellow one is the frequency curve when applying the standard UFS. A metric used here is the expected energy not served. For the standard UFS, it sheds around 11 megawatt-hour, while for the proposed UFS, it sheds less than half of the standard UFS. The main reason is that the local UFS strategy has to wait for the frequency reaching the threshold before reacting on power system imbalance, while the proposed method relies on the system fully observability by means of PMUs feeding in a suitable state estimation process, so it can react on system power imbalance as soon as possible. Therefore, with smaller amount of load shedding, the proposed UFS achieved the same frequency containment effect. The figure on the right side shows the load shedding results for the proposed method. Here you can see that the asymptotical prediction matches very well with the real one. In this slide, we have the results for scenario 2. In this scenario, the pre-contingency conditions for line 2 to 3 and the 13 to 14 are already close to the ampacity limits. From the frequency trajectory, we observe that the proposed UFS restrained the frequency nadir to a much smaller value. Indeed, this is because the proposed UFS shifts more progressively in order to respect to the line ampacity limits. On the right side, we have the line current magnitude. The red lines are the ampacity limits for line 2 to 3 and then 13 to 14. It shows that due to myopic to the grid states, the standard UFS has significantly violated the line ampacity limits. In contrast, the proposed UFS shed the optimized amount of load at the mean time with respect to the line ampacity limits. It is worth to note that although the ampacity limits are not violated asymptotically, they are indeed violated at the very beginning. So here we also characterized the computation complexity for the proposed OPF UFS. The theoretical worst case complexity depends on the number of nodes in the network and on the number of time steps in the considered prediction horizon. And we assessed the computation time using a MacBook Pro with the Groovy solver. Here we got an average of 1 second to solve this optimization problem. Therefore, the proposed method can run in parallel with the contingency analysis. To wrap up, we presented a centralized UFS scheme based on the OPF problem, whose constraints include grid constraints, a dynamic model of the frequency, power flow equations, and a model for voltage and frequency dependent nodes. The proposed approach is able to control the trajectory of the frequency to ensure that the voltages and currents do not violate safety limits. Then we validated the proposed approach by means of real-time simulation over a full replica dynamic model of the IEEE 39 bus power system. Then the results show that the proposed UFS scheme outperforms the traditional ENSO approach in terms of expected energy served and the grid constraints compliance. I would like to thank you for your attention, and Asja and I are here for your questions.
Okay, thank you very much, Asja and Yihui. So, we have one question from Carleton Coffrin.
Mm-hmm.
Did you see them? I can read it if you want.
Yes, I can see it now.
Okay. If time to collect data, run state estimation, and send control actions to the field while the dynamic event is underway.
Okay, so yes, thank you for your question. That's a good question. So as we said, we make the bold assumption that the method underlies a situational awareness system that is based on phasor measurement units. It is shown by state-of-the-art works on the state estimation provided by phasor measurement units that they run in the order of hundreds of milliseconds. Therefore, then we also take into account some time in order to send back the control actions to the devices that are making the under frequency load shedding actions. So we quantified these values in the order of 120 milliseconds finally. So we do believe that this is sufficient, and actually it is also less than what the standard under frequency load shedding scheme given by the NSOE recommends, which is in the order of 500 milliseconds in order to wait for the frequency to reach some, let's say, understandable values. As you know, we have to wait for some time in order to make a mean of the frequency measurements. Thank you.
Okay, I can say then. There is a second question from Kate Bell.
Yes.
Is it your idea that an optimization will be carried out as a fast post-fault action, or the algorithm would be run every time a new state estimation is received, adapting the settings of local ULFS controls?
Yes, and I see also something on top of that adaptation. Wait, I lost it. Okay, there was also something else, but anyhow, so the idea is that the method runs in parallel to contingency analysis. Having it run at every state estimation could also be feasible because, as we saw in the slide that Yihui was presenting, the computational complexity takes 1 second on a standard MacBook Pro. So I guess that with a bigger computation power, we could also go faster. So I would say that it would be good, of course, to run it every time a new state estimation is received, but the idea is to run it in parallel with contingency analysis.
Okay, thank you. And there is an anonymous attendee who asks, the sensitivity coefficient depend largely on the nodal injection and the frequency. Both of them must be varying during the ULFS. How do you update it? Can you please comment on this?
Yes, thank you. That's also a good question. So again, we make the assumption that we are working in an environment where we have a system state that is given by phasor measurement units that in parallel typically also can assess in real time the topology of the network. That is why we make the assumption that we can know all these parameters in real time. Once there is a topology change and once the system state changes, of course, we have to recompute the sensitivity coefficients, and that's exactly what we do.
Okay, I have only one question because we have only 1 minute. So about the standard ULFS you use to compare your method, it also includes frequency derivative thresholds or only frequency thresholds?
So in this work, we only use the frequency thresholds, but in our previous work, we also use the frequency deviation thresholds. So what is called the ROCOF in TMU wording, let's say. But for this specific work, we didn't compare it with our ROCOF-based UFLS.
Do you imagine the results are different, or more or less there is no...
I guess that we would have exactly the same problems as we have in the standard scheme, because again, the results are myopic to the overall grid state. So we saw that also with the ROCOF-based UFLS strategy, we can violate some ampacity limits of lines, for instance, or some voltage variations in the grid. So I guess that the result would be quite similar.
Okay, thank you very much.